Okay. For those of you who are tuning in, sorry about the maybe lighter color. And then as you can stand here, there's a glare here. Then there's a glare over there. But we'll do our best to navigate our way through this. Okay. The first types of problems that we had discussed were dealing with barometric pressure. Now, what we mean by that is this is what's doing the reading, okay? Atmospheric pressure is just what you would be experiencing outside. So what we'd see happening is I think it's a pretty fair presumption that, how do I want to say this? A pitot tube is an instrument that's on airplanes, and I think they're on diesel engines as well, because what that's doing is it's measuring the pressure, whether it's fluid for transmission fluid, or how fast that air is moving over that pitot tube. And that gives an indication of how fast that plane is flying because of the pressure given. So, and I don't know how many of them are on a plane. Does anyone here have aspirations of becoming a pilot? We have no Tom Cruises in here. Yeah, I thought that would be kind of neat, but I knew I wasn't smart enough at the time. Yeah, when we say that, it's not that we're lowering our standards. We're lowering the requirements. Okay. That's two totally different ways of looking at things, okay? So with this, the paper that you're going to get today, sometimes we deal with open manometers. These are a little more difficult. If it's a closed manometer, you just convert kilopascals to what, do you think? What is the standard measurement for pressure? Atmospheres, okay? So if it's a closed manometer, you just convert your kilopascals to atmospheres and you're done. And does anyone think they might know why? What's the difference between open and closed other than just the terminology? If it's a closed manometer, it has one extra step taken to it. It's sealed how? With a vacuum, okay? So again, if it was a closed manometer, then you just convert this to atmospheres and you're done. But if it's open, you have to do a correction for that, okay? And how do you know how to do that correction other than us just telling us? There is hopefully a clue in there that we discussed yesterday that when you do a correction that we hopefully have illustrated that you do it correctly. Because, okay, higher in the atmospheric arm, okay, does that stand out in your mind from yesterday? Okay? Not anodized aluminum, AA, or always awesome. Well, everyone's always awesome in here. If that was the A's we wanted to use, or 2 semester grades, A's and A's, we maybe hope, or maybe, I sometimes wonder, because I do see it reflected with some of you students, that has anyone looked on their report card and they think, oh my God, I've got a B in this class?
I'm happy I have a B in this class.
Did you notice that the ceiling is still there? And I bet if you walk outside, heck, the sky's out there too. It hasn't fallen. Okay? Because sometimes what happens is if we are not used to dealing with those types of hardships, and I think I said in another class, you're always going to appreciate something. You have to work harder for it. Okay? So with that, what stands out in your mind when you see atmospheric arm? And does the drawing help? I'm not a very good drawer.
Yes, the drawing helps.
Drawing helps, okay? So let's see, is there going to be, yeah, I think I can do it here. Okay? So again, we know this is open because that has not been capped off. If it was, well then it would be a closed manometer, which is much easier to deal with. So then again, maybe we have some sort of gas in here that's exerting pressure on this mercury. So when we say it's 77 millimeters higher in the atmospheric arm, is that left or is it right? It's okay. So it's on the right side. So we'll approximately put a different color in there. There. And not that the increments have to be that accurate, but from here to here, there is a difference of 77 millimeters, because that's what's given in the problem here. Okay? So what are we going to do with that 77 millimeters? We're going to convert it to something. And our correction is tied into this. So we have to get this into kilopascals. So how would we go about doing that? That's first, and then into kilopascals. Okay? So if we start with 77 millimeters, okay, go Philadelphia. So I'm using green. Fly, Eagles, fly. Okay? Some people are shaking their heads no. Why is that?
Yeah, there's no colors.
Okay. So with that, how many millimeters of mercury are in an atmosphere? 760. So does that go on the top or the bottom? Okay. So when you put these labels in here, then we know where the numbers have to go. For every 760 millimeters of mercury within a column, we know we're going to get an atmosphere pressure. So that gets us halfway home. So then 77 on top, 760 on the bottom. So now we're in atmospheres, but we want to get to kilopascals. So where does atmospheres go in our next step? For every atmosphere pressure, you get how many kilopascals? It's some people were saying it correctly, 101. Some people were saying it incorrectly, saying 101. So if you are repeating the zip code for Coleman, how many are saying 57107? It's 57107, right? O is not a number, but it's just, I don't know, social convention. 605. It's not 605, it's 605. O is not a number. Right? But again, therefore, it's just social convention that, 605. But all right. So upon doing this, what do we get for kilopascals? Multiplying 77 times 101 divided by 760. Okay, so that's approximately 10.27. Now we're in kilopascals. Okay, which means now we've got our correction. We just need to take that one last final step. And since it's in the atmospheric arm, we've got 87. That, you're right. Why? Yeah, you always add. If it's in the atmospheric arm, you want to add. So then 97.27. All right. So one of the aspects that we see here, one of the numbers has nothing to do with the problem. Yeah, we really don't. Well, yeah, I suppose you could say that we care where this is. Does anyone think they know approximately miles? How many is that? Yeah, 2¼ maybe, because there's 5280 feet in a mile. So yeah, so a little above 2 miles off of the Earth's surface. So what do we know about gases? The higher in elevation you go, the thinner it is, because we talked about that yesterday. If you've ever been in the mountains going hiking, you think, dang, I thought I was in better shape than this. So, and it's all about perception. Just like when you walk out, if we said, let's walk out of the building today, none of you are going to want to come back in. Kind of like the cattle get out, the cattle don't want to come back in. Darn critters, right? For anyone who's had cattle before. But anyway, but our perception of that, we walk outside now and we think, oh my God, this is nice. In June, if this is our temperature, what's our perception? God dang it, it's cold out here. Okay? So anyway, just like with physical science, the best thing that you can do, okay, is write down your given information. Now, that's after you've read the problem, because I know it's a little blurry on here. Okay, it says, in altitude of 12,280 feet, this balloon, or this Chinese balloon, was shot down off the coast of South Carolina. The pressure was 82 kilopascals, and the oxygen gas had a volume of 3,300 milliliters. And on the surface of the water, where that balloon was maybe collected, okay, we could presume that the volume was 4,250 milliliters. What was the pressure at sea level? Okay, if we know anything about how pressure works in vacuums, straws, even in flight, okay, temperature is certainly related, not in this process, but this is Boyle's law, which we had said, write that down. Pressure 1 times volume 1 equals your new conditions, pressure 2 times volume 2. Okay? So when we look at these 1s and 2s, okay, it looks like it's something new, but it's really not. Because, oh boy, physical science, that was a great time to be in this class, right? You don't need to write this down, but what did acceleration equal? You remember? Something about velocity. But which one's which? Which one comes first? So what we mean by that, those little subscripts are important because it's telling you which one's which, okay? So this is a final velocity. There's your initial velocity. So when we look at this, the concept has changed just a little bit because 1s are your initial conditions that we would see here, and 2s are your final conditions, okay? So we're just expanding upon that concept just a little bit. Okay, so where is our first, where are we comparing this to? Where did the balloon first start? Up at altitude or down below?
Literally.
Up top or down on the water? Yeah, up top. Okay. So once you've read the problem and you have your formula, okay, so we want to put these variables in here. Just bringing back good memories of physical science? Yeah, of course. This means yes. I'm sure everyone's going to nod their heads yes. Okay. So what was our first pressure that we saw? At altitude, what was the pressure on that balloon? Okay. That's right, but we want that in what though? We want those in atmospheres, okay? Pressure is going to be in atmospheres. Volume can be in liters or milliliters. You don't have to do a conversion for that. Does anyone think they know why? When you are converting milliliters to liters or vice versa, what are you doing with the decimal? You're just moving it, so you really don't have to do any true conversions. That is completely different than putting this into atmospheres. So how do we do that with our kilopascals? And once you get really proficient at this, you probably don't have to do this dimensional analysis. You can just do something a little simpler. But how do we get this into atmospheres then? Do what? Okay. So what is our standard unit of pressure for converting kilopascals to atmospheres? And you can say 101. I just think, no, it's 101. So what I'm saying going forward, if you have to do that, there's nothing wrong with this. Just put that under your 82 because you're basically doing the same. Butchered that. See, I think I'm sometimes make 8s better when I put the 2 circles, but maybe I should just do that, I guess. Okay. These are the same process that you're doing here, so it's probably somewhere around 0.8, probably not even quite 0.8. Okay, 0.81, 0.81 atmospheres now. Okay? Then what was our initial volume? What was it up at altitude? 3,300. Okay? You can leave it in milliliters. Then once that balloon was shot down, approximately we're assimilating that the volume at sea level, or where it landed, would be our new set of conditions, which is 4,250. So then what was the pressure on the ground? A couple things that you can do to help point yourself in the right direction, okay? And that is, and it's kind of like doing these configurations. If we were to do, for instance, we'll keep it short, something like chromium, which is element 24. So you know we're up to argon, 4s2, 3d, was it 5? No, 1, 2, 3, 4. So to point yourself in the right direction, what is 4 plus 2 plus 18? 24, right? What's the atomic number for chromium? So you can check to see whether you're doing it right, and this is in a similar manner. This is proof to illustrate that. Okay. So what did we say yesterday in even this hiking example? If you take off at ground level and you start walking up a steep incline and you're getting higher in altitude, what's happening as you breathe? It's getting difficult and more difficult. It's not that you can't breathe. It's just that those oxygen molecules are further and further apart because the pressure is less. So what we see happening is if we know if the pressure is going down, okay, what must the volume be doing? It's an inverse. It's going up, okay? So one way of looking at that, okay, in pressure, if pressure is going down, volume then is going to be going up. Or if the pressure is going up, then the volume is going to go down, okay? So we'll come back to this in just a moment. Okay, So how do we solve for this? Once you have this set up, you just do what this formula tells you to do, and that is to do what? We got our initial conditions, 0.81 times, okay? Oh, I put it in liters, didn't I? Not even liters. That's hectoliters, 3,300. Okay, equals, so what's on our right-hand side? What is our second volume? 4,250. And then P2. That's what's left over. So once you multiply these two, divide by 4,250, you will have your new pressure then. And what do we, how much? 0.63. Is that right? Is that some? Okay. Okay. And then that is going to be in atmospheres. Well, when I made this up, maybe that wasn't quite accurate, but let's see once what happened, okay? So what did the volume do? It went from 3,300 to what? It went up. So what that tells us is if the volume is going up, what should the pressure be doing? Be going down. So we started at 0.81 and went down to 0.63. So that's one of the things that you can use to tell yourself if you're moving in the right direction. Okay? And for anyone who knows anything about car tires, of course, this time of year, it's not so bad now, but when we had that cold snap, Charles' gas law is just a little, it's similar, okay? But when gases get cold, not gasoline, but gases like what we breathe, when temperature goes down, what does the pressure in the volume in your tire do? That goes down as well, okay? So that's just a clue, again, that you can use to help yourself out in this manner. Okay, so this will be handed out here shortly, due on Thursday, and you have a little bit of time to work on these, and you have a little bit of time tomorrow, but I wouldn't bank on that. Although the Charles Law paper, that isn't quite as long as this one. And then perhaps next week there's actually an activity that we can do that we do with Charles's gas law over in the lab. But on Friday, we'll probably have a combined gas law paper. So anyway, so that's all I have. So we will catch up to you next time.